Hello and welcome everybody to this new episode on news in the world of FICO Xpress. Today we will look into what's new in the latest release, Xpress Solver 8.13, which has been available for download at the usual places since December 2021. As you might be aware, FICO Xpress optimization consists of various components, all built on top of each other and nicely integrate within each other. And with your application, you might enter the stack that we see here at different levels. I, for myself, work down here in the lowest, the lilac level, on the heart of Xpress, the solver core. In the next round about 30 minutes, I would like to tell you what news and new features there are to make this heart beating more vigorous than ever. Us developers in the solver team have three main drivers: performance, features, and robustness. These are the things that we work on in each and every release. First and foremost, we strive to make our wide variety of optimization algorithms and solvers for various types of optimization problems faster and faster with every release. Secondly, we want to make your life more convenient and open new optimization applications by offering new modeling capabilities, enhancing analysis tools, and other valuable features. Finally, we will always aim to further improve our solver's numerical robustness, with Xpress already being the most deterministic and probably the most numerically robust solver. In this presentation, I will describe the improvements made to FICO Xpress during the past release cycle of 6 months. The focus of this release is MIP performance, in particular cutting performance, after the last release, 8.12, had been about heuristic performance. Check out the presentation about 8.12 here on this channel. But also other parts of the solver, like branching and pre-solving, saw some nice improvements. The two big topics for today will be the first two on this list: learning to use local cuts and handling indicator constraints. When done with the MIP advances, we will describe the innovations made to the barrier algorithm and our nonlinear solver. And finally, we will present changes made to the file handler, which now supports various compression tools, most likely also your personal favorite. And towards the end, we will present the performance numbers and make an announcement of a new Xpress initiative. Without further ado, let's start with looking into the latest developments of our MIP solver. Our first topic involves a crucial binary decision for the use of cutting planes. Here we see a typical MIP problem: an objective function to maximize, a few linear constraints, and the requirements that both variables should be integer. This is the kind of mathematical problems that Xpress solves every day, just a million times bigger, and coming from applications like portfolio optimization, unit commitment, supply chain management, scheduling, routing, network planning, energy production, well, you name it. On the right, we see a graphical representation of the problem. 2 times because there are 2 principal algorithms to solve such problems. The first is branch and bound, where you split the search space into 2 parts recursively until you find a feasible or even optimal solution. And the second one is the cutting plane method, where you add new valid constraints iteratively until you converge to the proven optimal solution. If you want to learn more about branching and cutting, there are videos available on the state of the art in either technique as part of the COX Work lecture series on this channel. I will leave a link in the description. Well, back to business. There are 2 meaningful ways to combine these 2 algorithms: cut and branch, so first cut, and then do a full branch and bound search without cutting, and branch and cut, which starts out pretty similarly, but then keeps generating a few cutting planes at individual subproblems of the branch and bound search, on each of them or only on some selected ones. And the second one, branch and cut, is typically the method of choice. It is what we at Xpress and the general optimization community really have been doing for over 20 years. But if you look a bit into the details, you will actually find that it's only about half of the instances for which this is really the better choice. For almost a quarter, this generation of local cuts hurts performance of the solver, and for the others, it doesn't really matter. This means that for every instance, we should ask ourselves whether we really want to generate cuts for it during research or not. This is a crucial question because, indeed, cutting planes represent an essential component of the branch and cut algorithm, and without them, the solve could be unsuccessful in many cases. On the other side, however, the use of cutting planes at internal nodes blocks some other solver features, such as conflict analysis. given that they make the use of this technique too complicated. Hence, instances that would benefit more from conflict analysis than from local cuts could be at a disadvantage. Moreover, the generation of cutting planes requires a non-ignorable computational cost, and having them in the relaxation slows down the LP solver. So in other words, when cutting planes are not particularly effective, they can be a burden to the solving process. Ideally, we would be able to predict at the beginning of the search which variant will perform better. And this leads us straight to the idea to train a machine learning model to predict whether the use of cutting planes within the tree search might be beneficial for the solve or not. And that's not an easy task, as you can imagine, but for the latest Express solver release, we trained a random regression forest to achieve exactly this. A random forest is a machine learning model which consists of multiple decision trees, whose individual decisions are averaged to give rise to a single final decision. We used over 3,000 customer instances for this training and made the final decision by not only looking at the random forest average prediction, but also having a majority vote from the individual trees. And as features, we use static features of the model instance, semi-static features like the density and the conditioning, which already depend on other solver choices, and there's an important dynamic feature, the performance of initial cutting done on the whole problem. In the plot, in the lower right corner, we compare our model with some human design strategies in terms of the shifted geometric mean of the runtime, and for different values of the threshold that marks the separation between the two methods. This is in particular a crucial hyperparameter of our decision process, and it is used for the predicted speedup factor as a switch between the two methods. The dashed lines in the plot represent from top to bottom the three strategies: never cut, which always chooses to not cut for each input problem, always cut, which always chooses to cut, and perfect oracle, the optimal strategy that for each problem always discriminates correctly between the two alternatives, hence representing the best choice that we can achieve. And the continuous curve instead corresponds to our learned random forest. First of all, it is evident that always cut, also being on average much better than never cut, is far from being the optimal strategy for our decision. Moreover, we can observe how the performance of our model converges on the left to the one of never cut, while on the right to the one of always cut. And by moving the threshold to the negatives or to the positives, indeed, we clearly bias our decision towards one method or the other. Hence, we force our model to imitate one of the two strategies. It is by looking at the behavior of the curve around zero, however, that we can grasp how influential our decision can be on the performance of the solver. The runtime of the random forest indeed reaches its minimum below the one of always cut, meaning that the model is effectively able to improve the solver upon the best of its competitors and to close the performance gap between this competitor and the perfect oracle. More precisely, the learned model provides a 2% improvement to the average runtime of the solver over our entire benchmark set, as you can now see in the table at the top. And this improvement, however, rises to the value of 15% over the affected instances. And these are the ones that do not benefit from the use of local cuts, hence the ones for which the random forest effectively changes the behavior of the solver, which otherwise would have used local cuts as in its default configuration. And in terms of nodes, instead, the introduction of our random forest into the solving process causes an increase in the number of nodes explored during the search. This is, however, not surprising, given that cutting planes improves the dual bound and, consequently, help in node pruning. Hence, by deactivating them, the solver obviously tends to explore a larger number of nodes. So overall, the learned model positively contributes to the performance of the solver. Our next topic addresses the way in which indicator constraints are handled inside Express. But before we go into the details, let's first talk about what indicator constraints are. Indicators represent a special type of constraints, which model if-then relations. The simplest case is given by the relation between two variables, in which typically y is a binary and x1 is continuous. Such an indicator relation states that if the binary is equal to 1, then the continuous has to be equal to 0. Otherwise, it might take any value within its domain. Often this is also written in the format y implies x1 equals 0. This is the error that you see there, where y is called the indicator variable. In the general form, however, the indicator variable y implies not only the value of a single variable, but the whole constraint of the form A transpose x less than or equal to b. In other words, such a constraint is enforced when the indicator variable is 1, otherwise it can be relaxed. And indicator constraints can be used to enforce a subset of a set of constraints. For example, suppose we want that at least 5 out of 10 constraints have to hold. Then for each of these 10 constraints, we can formulate them as indicator constraints with a different indicator variable. By taking the sum of the different indicators greater than or equal to 5, we can enforce that at least 5 constraints hold. It does not matter which ones. Moreover, indicators can also be used for adding reward or penalty terms when a certain constraint does or does not hold by putting the indicator variable into the objective. An indicator constraint can also be linearized by using a so-called big M formulation, at least if there is an upper bound on the quantity A transposed x within the domain of x. If the value of the indicated constraint can grow arbitrarily large, a reformulation might not be possible. If there is such a bound, however, the indicator constraint can be written as the linear constraint A transposed x less than or equal to b plus 1 minus y times a big M constant, which is large enough, whatever large enough means exactly. In this formulation, if the indicator variable is 1, then the last part of the right-hand side vanishes, implying that A transposed x has to be bounded by b. Hence the linear constraint has to hold. On the contrary, if y equals 0, then the bound b is enlarged by big M, where the constraint gets effectively relaxed. And in this case, indeed, A transposed x can take arbitrary values. When using big M formulations instead of indicator formulations in the model, the value of M has to be chosen carefully. A trivial choice, and one that a solver like Xpress can take automatically, is of course the maximum of AX minus B. However, such a much smaller value of M might be feasible if there are other constraints in the model ensuring that A transposed x cannot grow arbitrarily large. So this is something that only you as a modeler might know. And when you decide to use a big M formulation directly, you should take care of finding good, meaning small, big M values. But let's now come to how indicators were handled in Xpress so far, and afterwards how they are handled now. In previous releases of the solver, we could only deal with linear indicator inequalities, while equations and range constraints were split. Indicator constraints were linearized during pre-solve via the big M method that we just saw, at least when the big M was somewhat reasonably small, something like 100,000 or less. If this M was really small, we even dropped the original indicator constraint and only kept the reformulation. Otherwise, we kept both to make sure that numerics were satisfied. If big M was really large, the indicator constraints were not linearized at all, and we only kept the indicator. Essentially, after pre-solving, there were 3 different states in which the indicator could have ended up, and this depended mostly on the maximum activity of the constraint that is indicated. Then, during the search, all the indicated constraints were pulled out and transferred into a separate pool. Hence, they were individually reactivated, that is brought back into the matrix when the corresponding indicating binaries were selected for branching. Also, these constraints were tightened when better big M's were available, hence they were reloaded into the matrix as new constraints, possibly in addition to other indicator constraints already occurring somewhere else. Moreover, given that the indicators were not part of the matrix until they were reactivated, we needed to have specific code to perform every activity that involved the use of these constraints, such as bound propagation or considering them in heuristics and so on. Okay, so that's gone now. In Xpress 8.13, we have a new way of handling indicators. First of all, in the new server release, we are able to handle more types of indicator constraints. In particular, equality and range linear constraints are now supported natively by the solver. In pre-solving, actually not much changed. we still apply the usual techniques, that is, we linearize such a constraint by means of a big M, and if this M is small enough, we drop it completely. The substantial change in the new release of the solver is in the actual MIP search. Okay, recall, in the previous version, we would only have added an inequality constraint into the problem when the indicator variable, the binary y, equals 1, while in the new version, we always load the indicated inequality by means of a slack variable, in which we put a lower bound when we want to activate our constraint. This allows us to not having to change the coefficient matrix on the fly, given that by simply using some free slack variables, we can carry around all indicator constraints. And in the particular case in which the indicated constraint contains only a single variable, we do not need to add any linear constraint, but simply impose a bound on this variable. Every time the indicator variable is fixed to 1, while branching, as well as while performing bound propagation, we only need to remember to set a bound on the slack variable of the corresponding indicator constraint. By this procedure, indicators very naturally integrate within all other solver routines, be it the named propagation, no extra propagator needed for indicators, or heuristics, or cutting. They are essentially just a linear constraint, but one that is not necessarily present in the LP, but has its own rules when to be added to the LP and when to be removed. One disadvantage of this reformulation of indicator constraints is that we need to preload all of the constraints into the problem. And this might slow down the LP solver a bit. I mean, not by the fact that you have to conduct additional iterations as the constraints are inactive, but all involved data structures will be larger. Hence, allocating and copying will be more expensive. And in some cases, you might have to pay with cache misses. However, thanks to the fact that the indicator constraints have a free slack variable, the factorization of the basis matrix in the dual simplex only has a single one for that particular basic column. This means that the impact of an indicator constraint on the simplex algorithm should not be too large, as long as this indicator is deactivated. On the other side, this new way of handling indicator constraints facilitates us to generate cutting planes from the indicator row directly, given that we have at least a finite big M. Moreover, the bounds on the slack variables can be more easily integrated in other parts of the code, given that we already have in place mechanisms to use variable bounds. And in general, it is fair to say that it is much easier to work with this new structure. As a consequence, it is much easier to allow other types of indicated constraints. And of course, we took this chance. And we extended the set of constraints that can be used with indicators. So, this is a great new feature that opens a whole new set of possibilities for modeling mixed integer programming problems. We can have, for example, convex quadratic constraints, which are simply handled as normal quadratic constraints, again with a new slack variable attached. So this is really the same trick as for linear constraints. We can have conic constraints. Conic constraints generally undergo a special reformulation, which generates a linear linking constraint. And this linear linking constraint is where we hook in with our new indicator representation. And finally, we allow for general nonlinear constraints, which are reformulated in the NLP presolve, similarly to the linear case. In other words, any kind of constraint that the solver normally supports can now be turned into indicator constraints. Full stop. Okay, this was admittedly quite technical. So let's switch topic to a nice performance boosting technique: history cost transfer. We looked at the two main ingredients for solving MIPS, namely cutting and branching, and already saw a cool novel feature for cutting. So let's now come to branching. Branching is one of the most delicate topics in mixed integer programming, as the choice of branching variables will decide on whether the search tree size can be kept under control or whether we get into an exponential blow-up situation. Here, one typically relies on expensive initialization techniques and later on statistics from past branches. Simple idea: what used to work great in the past hopefully works again. Therefore, we store the average objective gain that we saw from branching on a variable, scaled by the fractionality of the variable. The history costs of a variable will then be the average over those unit gains. And later in the search, they are typically quite reliable, but as you can imagine, in the beginning of the search, they lack the information from previous branches. Curiously, for many MIPS, we will restart the search after a few hundred or 1,000 nodes. This is first of all for enabling additional pre-solving, which can often shrink the problem size tremendously. Secondly, this is used for a change of strategy. For example, we will use a more expensive branching strategy afterwards, which, however, still relies on history costs. So, we asked ourselves whether we should try to recycle the history costs from the first one. Well, obviously, you can argue that those might be something like a global characteristic of the problem, and what was a good branching indicator before the restart should still be after. In fact, this is not so clear, because your search space will be structured in a completely different way, and the old history costs might not reflect this. Also, the whole idea of restarting is about A, the problem changing a lot by additional pre-solves, and B, trying different strategies than before. We should just do the same thing sounds wrong in that light. So, we came up with a middle way of treating the complete history statistics of a single variable as if they were a single observation on a new problem. Thereby, they still serve as an initialization, which is the Achilles heel of history cost branching, but they are quickly outweighed by new observations. Together with the ones already illustrated, many other smaller enhancements have been provided to the MIP solver in the current release. Although all these minor new features individually improve performance by only a few %, altogether they provide a significant overall contribution. Different changes have been made to the cutting procedure executed during the solve. In particular, we have implemented a more aggressive removal of cuts that are no longer active and worked on the heuristic that tries to combine constraints when mixed integer rounding cuts are used. We have learned whether to use local cuts as already presented and improved the cut limits in the cuts selection phase. Next to the discussed transfer of history costs, we now have refined our strong branching strategy. Like before, we strong branch at most once per variable before a restart, and after a restart, we strong branch at least 4 times. In the new release, in particular, we try to not strong branch on the same variable too many times for nodes that are close to each other, in order to diversify the way in which strong branching is performed for each individual variable. And after the 8.12 release, having focused on heuristics, the new release has not seen many changes in heuristics. The only improvement has been made to the rinse heuristic, which was previously called at a fixed frequency, while now it is called more frequently at the beginning of the search when good solutions are more needed. Other changes consist in a restructure of some pieces of the code. As you see, sometimes they also contribute towards performance. In particular, one such change is represented by the replacement of the deterministic proxy to wall clock time used in MIP with the one used for concurrent LPs. Moreover, the code for click covers also has been refactored. Finally, some improvements has been provided by the dualization of LP. This is in particular an LP feature which, however, has some relevant impact on the MIP solver. Precisely, the change consists in avoiding to create singletons when they are not needed. This directly brings us to the topic of LP improvements. For the barrier algorithm, there's now the default option to perturb the objective function in order to push the barrier solution to one of the corner solutions. This hopefully reduces the number of super basic variables and consequently the number of pivots while performing crossover. On the overall set and on the hard instances, the improvement provided by this change is a modest 1 and 2% respectively. But by restricting the test sets to the affected instances, however, these values increase to 11 and 59% respectively. So this new option can be adjusted by means of a dedicated control that we have introduced. Moreover, in the sifting algorithm, we have introduced a new control that allows to specify the behavior of the pre-solver on all those sifting subproblems that are iteratively solved by the algorithm. And finally, there has been a little rework around our AVX2 specific code, precisely around the vectorization handling for AVX2 instructions. Note that AVX2 support is off by default, given that it takes a different solve path than the standard AVX or SSE2 code. This is why its activation is left as a conscious choice that can be taken by setting the CPU platform control to -2. If your computer supports AVX2 and you solve LPs by barrier, we typically recommend to do so. the nonlinear solver has also seen some relevant improvements. Those of you who are frequently attending these presentations here on the Mixed Integer Programming channel might be aware that we have been working on extending our pre-serving capabilities further and further. This has mainly focused on getting more and more global reductions from the linear core of the problem, instead of applying them only on the stepwise linearizations of the SLP approximations. Not only is this more efficient, but it also allows for adding some more reductions that we would only want to do on a global scope, but not when there are local approximations mixed into the linear system. While our work here focused on the linear core of the nonlinear problem, it was of course not restricted to this. So, 2 releases ago, we mainly added primary reductions, while in the last release, it was about dual reductions for the nonlinear solver. And in this release, we concentrated on integer reductions, or MIP reductions. To give you an idea of what I mean by an integer reduction, let's consider 2 examples, coefficient tightening and GCD reductions. Coefficient tightening is a technique that considers binary variables in linear constraints. Binaries with a relatively large coefficient in this constraint. Relatively large in this case means that the constraint will get redundant once that single binary is fixed to 0. And in this case, we can tighten both the right-hand side of the constraint and set coefficient of the variable. This is a disjunctive argument. For fixing xi to 0, the new inequality is still redundant, but tighter. And for fixing xi to 1, we get the odd inequality. Since xi is binary, it is sufficient to check these 2 cases. And the other example is a GCD reduction. If all coefficients in a row with all variables being integers share a common divisor, then we can clearly divide this row by the common divisor and we'll still get a valid row. The interesting bit is when the right-hand side is not divisible by the GCD. In this case, we can validly round it down, thereby strengthen the constraint. This procedure can be extended to non-integral GCDs. By the way, for example, if all coefficients are multiples of 1/2, but the right-hand side is not. So, GCD reduction is an example for a rounding argument. Thereby, we covered 2 of 3 principles of integer reductions: disjunction, rounding, and lifting. And all of them exploit the discreteness of integer variables. So as said, this is relevant for a one-off pre-solving of the whole nonlinear problems, and it leads to a substantial improvement to the solver. We measured this in terms of the primary integral, which is our usual measure to evaluate performance of the nonlinear local solver. Another big improvement for the continuous side of nonlinear has been made to the convergence of hard mixed integer quadratic nonlinear programs. And finally, we have introduced to the nonlinear solver an ability that was released a long time ago for the linear case, namely the ability to randomly permute a nonlinear problem. This new feature is particularly useful for performance measurements when you work with a relatively small test set with only a few instances. It helps in handling the phenomenon of performance variability, hence the random change in performance when you slightly change the starting conditions for an optimization problem. Performance variability can be seen as noise in your benchmarks, and inflating your test set by using random permutations of the problems at hand will help to tell noise apart from actual improvements, because noise will cancel out over many instances where actually improvement will not. Obviously, this is also very much in our own interest for development, since it guarantees more robust solver development and tuning. And several substantial changes have also been made in terms of usability. One of them consists in the support for compression, both in reading and writing problems, as well as all kinds of solution files. gzip support was already available in Express and is directly built into the optimizer, delivered as part of the library. We have extended this now, and we now support also external compression tools. Hence, you need to have one of these tools installed on your system, and then you can use them with Express directly. We do the obvious thing and look at the extension of the file, and if we can find the required tool for the extraction, we use it for compression and decompression. For example, if the file name ends with .7z, we look for the path of the 7zip control tool and use it for compressing or decompressing that particular stream. As you see, 7zip will be sufficient for all supported types, and it is in any case a great tool to have installed. I'm a fan, admittedly. Another minor change consists in the automatic initialization of a new problem as an empty problem, unlike in the past, where the user needed to call a dedicated command before starting to add rows and columns. Moreover, 2 new functions have been added to query and clear the status of special constraints such as quadratic, delayed, model cuts, indicators, or nonlinear. These new functions, in other words, complement an already existing function that allows to label a constraint as a special one, essentially by attaching a flag to the constraint itself. Another feature that has been requested a few times, and that is now released with the newest solver version, is the possibility to set a time limit depending on when the last solution was found. More precisely, we have introduced a control to fix the maximum time that the solve is allowed to keep running since the last incumbent was found. If from the last incumbent no solution is found within that limit, the search is stopped. Note that this only becomes active once a first solution has been found. It is also worth mentioning that our MATLAB interface has been extended to support indicators, piecewise linear, and general constraints. These constraints are loaded through the MIP structs argument, which was previously only used for special ordered sets and had a different name. But that means that the interface has essentially been preserved and only extended in functionality. And finally, 2 convenient environment variables have been introduced to enable API call logging and to decide the location where to write the file. That functionality is very convenient for debugging and was previously done by placing a specifically named file in a certain location. Finally, let's come to the most interesting part of every release presentation: performance numbers. A year ago, we released Xpress 8.11. Release presentation available on this channel. And this table compares our new 8.13 release against 8.11. It's a typical year-on-year improvement table. These are numbers on our benchmark set consisting of a mix of public and client instances. Client instances are sampled to avoid any type to dominate the benchmark, similar to how MIPLib 2017 was constructed. Mentioning it, MIPLib 2017 benchmark makes up about 20% of our internal MIP benchmark set, with the rest being mainly client instances. We have a similar setup for our LP and nonlinear tests. We split the MIP evaluation into 2 sets: the benchmark set, for which we measure time to optimality, and the PDI set, which mainly consists of unsolvable models, for which we measure the prime dual integral. This is also why the greater 100 second column does not exist for the PDI set. Almost every instance would fall in this category. For nonlinear problems, on the other side, it is left out because we do not have enough models that would fall in that category to make a trustworthy statistic. Looking at the performance, we can see modest improvements in the LP solver, given by the enhancement provided to the dualization and the barrier. The concurrent has also slightly improved in consequence of the changes in the deterministic timer. Conversely, relevant improvements are shown by the MIP solver in the number of solved problems as well in the average runtime performance. This is certainly the highlight of this table. Our MIP solver for more challenging problems is about 35% faster than a year ago. Across all instances, which include some that are trivial to solve or will be solved by the initial LP, the overall speedup is still 20%, which is a very strong value. Note that this benchmark set consists of 1,110 instances, each solved in 5 permuted versions, such that we get a total of 5,550 measurements to draw these mean values from. In the unsolvable PDI set, we observe an improvement of 9% in prime dual integral across all instances. Note that this does not include the impact of viewer emphasis, a non-default feature released in 8.12 that would easily add another 25% PDI improvement on top. The contributions provided to the MIP solver are also reflected in the MIQP, MIQCP, and MISSCP solver, hence everything convex quadratic. It shows a 9% improvement over our test set. And finally, the enhancements provided to the nonlinear pre-solver in the 8.12 release, combined with the one given in this release, contribute to very encouraging advancements in the nonlinear solvers. Given that this release we mainly worked on MIP features for nonlinear, it is just logical that the improvements in MI-NLP are about twice as large as in NLP alone. And now, it is my honor to announce a project we have been preparing for some time and that got finally set up now, the Xpress Best Paper Award. This will be an academic award that honors great scientifically valuable contributions that use FICO Xpress. This can be a paper in one of the well-known OR, MS or optimization journals, but also a paper that is published in a thoroughly reviewed conference proceedings. It can be on solving new types of problems or developing new application-specific algorithms that solve optimization subproblems via Express. Or it can be a paper on new mathematical optimization methods based on an Express callback implementation, or really any other imaginable research where using Express optimization products played a significant role. The authors of the winning paper will be awarded a prize of $1,500, and for the first edition of the award, all papers will qualify that are published within the years 2021 or 2022, so there's a 1-year overlap. As you might be aware, some journals have a system of online first publications. Those will qualify as well. I might point out here that MPC, Mathematical Programming Computation, just established a short communication track with a fast review cycle that might also be a possible outlet. As of the publication of this video, there is still 10 months to go to the first deadline. So you can take the next weekend to think about a cool research topic, start writing a paper, and when the review process is not too tedious, you have a good chance to qualify for the first edition of this award. And if the review process does take longer, or the submission deadline for your favorite conference has already passed by now, well, then you will have a chance in 2023, as we will continue this award event. And as you see on the slide, the scientific committee to judge the submissions has already been nominated. And if you have any questions, you can send them either to the named email address, or I will also be happy to answer them personally when you send them to my email. And if you wonder how to get access to Express products, that's the perfect time to point out our community website, where you can download a community license and start playing with the software immediately. If you are an academic, you should consider our academic partnership program, which grants you full licenses of all Express solvers, given that you work at an academic institution or that you want to participate, say, in an academic award involving Express. And the community is also the place to go when you want to learn more about Express and the technologies it implements. Check out our community website to learn more, browse the forum, view training material, and in particular, read the blogs, like our blog on Express heuristic emphasis mode, or a blog on the right choice of hardware for optimization that has been published 2 months ago. And through the FICO community, you also have access to the Product Ideas portal to submit your suggestions for product enhancement. You can also follow us on Twitter to get informed about the latest news on Express. And finally, if you want to get an in-depth understanding of some of the cool features implemented in Express, you can read our papers. They appear in top-tier scientific journals and are additionally available as free-to-read preprints. I just listed some of the most recent ones here. 2 more are currently in preparation. And this brings us to the end of today's presentation. Feel free to send me an email if you have any questions, and see you in a few months for the next release presentation. Bye bye.